Good morning. I just made a Canvas announcement that I'm recording the lesson right now and we'll be posting that on Canvas by 11 a.m. this morning. You probably just got the notification. In this video, I'm going to go over section 3.1 note. I did post a blank copy on Canvas for you, so if you want to print it out and go through the notes with me in this video, that will be really great. It's a little long, 7 pages, and last week I started posting videos on YouTube, and if it's long, the processing just takes forever. So I may cut this video into like 2 or 3 smaller pieces and post like 2 or 3 videos on Canvas instead of just one long big video. Okay, now after we go over this 3-point note together, I want you to try 3.1 problems. I posted that also on Canvas. You have 2 problems to try after today's lesson. And I did say by March 29th, but the Sunday, but it will be great if I can get it soon so that I don't have to grade 20 or 30 assignments on Monday morning. Homework 3.1 is also open on my math lab for you. So you only see about 3 items right now, but you will also see the video links. And please come back on Thursday for Thursday lesson, okay? All right, let's get started on this note. Right here. Okay. Section 3.1 is about using first derivatives, which you all know how to find, to classify maximum and minimum values. And the goal is to really sketch the graphs. Like I said, I may probably just go over like the first 3 pages on this video and start recording another one so that the videos are not too long and not too big. But let's read the learning objectives. The first one is to find relative extrema, either minimum or maximum, of a continuous function using the first derivative test. And we'll read about what that is, and we'll use that in our examples 4 through 6. Never mind, like I think 3, 4, 5, and 6. We'll use the first derivative test on examples 3, 4, 5, and 6. And the classwork problems that you will do for me for lesson 3.6 is actually using that first derivative test. And we'll sketch the graphs of continuous function. We'll do some sketching too. Okay, all right. The first definition, which you already know, when the function is increasing or decreasing. So first, function f is increasing on interval I for every a and b and I if we have a smaller input value. If a is smaller input, then the output should be also smaller. F of a will be smaller than f of b. So you put a small input in a function and you get a smaller output compared to the other input and its corresponding output, then we can say this is increasing. It's just notation, but in a picture like this right here, you see A is smaller than B because A is on the left side and B is on the right side. Notice the f of B is higher, right? And f of A is lower. So that's really a function that is increasing. A function is going up from left to right. And if we have that, we call that an increasing function. Or increasing interval, I should say. All right, how about decreasing? We say f is decreasing on I for every a and b in I. If a is less than b, then f of a is greater than f of b. So what this is saying is a smaller input is going to give you a bigger output. So in this picture, you see how A is smaller than B because, like, if you want to put like a random number here, or A could be something like 2, 3, 4, 5, 6. B can be something like 6. But notice A has a higher Y value, a bigger Y value compared to the Y value for B. So if we have a picture like that, it's going down from left to right, we say that the function is decreasing. You've seen this idea before from pre-calculus, but just kind of wanted to talk about that first. Now, let's connect some calculus to this, okay? Now take a look at this picture for me. The first one on the left, it says slope of secant line is positive. Well, A from left to right, from A to B, notice the slope of the secant line is going up from left to right. Well, if the slope of the secant line is positive, then we're going to say this function is increasing. So if I say let f be differentiable over an open interval I, say that if the derivative, if f prime is of x is positive, look at the way that I'm writing this. If f prime of x is positive for all x and I, then f is increasing over I. It's just saying if the derivative is positive, then the function is increasing. Alrighty, let's look at the second one where we have a decreasing function. It's going down from left to right. And if you take a look at the secant line, it's going down from left to right, right? A line that's going down from left to right has a negative slope. So the slope is the derivative, right? So if the derivative, if f prime of x is less than 0, in other words, this is negative slope, negative derivative, for all x and I, then f is decreasing over I. Okay, I hope this is making sense so far. Let's use this idea in example number 1 and 2, okay? So, making some notes on the side. Positive derivative means the function is increasing. Okay, so make some notes. If you have negative derivative, I don't know if you guys can hear my dog snoring. All they do is sleep, I noticed. Negative derivative means the function is decreasing, okay? Or I should say f of x is increasing and f of x is decreasing. So we'll use this idea to look at number 1, to try number 1 and 2, example number 1 and 2. And I saw 2 problems just like this on your homework, so this will be great. Example 1, the graph of the derivative f prime is given. Guys, this is not our f function, this is the derivative. Okay, graph the derivative. Look, this is a linear function, so we're thinking that the original f of x is probably like a quadratic function. Okay, use the information in the graph to determine where f is increasing or decreasing, and the x values of any extrema, then sketch a possible graph of f. Okay, all right, so let's take a look. This is a derivative function. This is a derivative function, and all we really care about the derivative is whether this value is positive or negative in order for us to tell whether it's increasing or decreasing. Look at this for me, okay? Positive derivative means it's above the x-axis. So to above the x-axis, these are gonna be positive derivative, right? And below the x-axis, smaller than 0, these are gonna be negative derivative. Okay, so where is the derivative positive? Let me use a green highlighter. Guys, I paid like 8 books for this app, so I'm gonna use all the colors I can. All right, take a look. This section that I'm highlighting, you see how that section is above the x-axis? What we know is that this is where f prime of x is positive. This is where the derivative is positive. Derivative is positive on, let me write the interval here, okay, using the interval notation. Negative infinity to Now, it stops being positive at what number? 1, right? So, f prime of x is positive on this interval negative infinity to 1. And what that means is the function f of x is going to be what? Increasing on the same interval. Okay? Positive derivative, like I said again, positive derivative right here means that f of x is increasing. So just because this little green section that I highlighted was above the x-axis, I know the function is increasing on negative infinity to positive 1. Okay? Alrighty. And if you're thinking this line is the function itself, then you're not going to say that because this line is going down from left to right. But this is a derivative function. And what you should be careful, what you should be really doing is which section is above the x-axis and which section is below the x-axis. All right, let me highlight the other section. Below the x-axis, what I'm highlighting in red right there. Now notice, guys, this is where f prime of x is negative, right? That means that derivative is negative. Derivative is negative on the interval what? From positive 1 to infinity. And what this implies is that our function f of x is decreasing. Okay, so this function f is decreasing on the interval 1 to infinity, and infinity. Oh my gosh. And it's increasing on negative infinity to 1. Okay, now that special point, remember how 1 was that special point where it was 0, right? I'm going to go ahead and do the sketch of a possible graph of f first, okay? We're never going to have an exact graph, but what we can do is something like this. At 1, that's where the graph will have a little turn, right? That's where the graph will have a little turn. So I'm going to go ahead and sketch a graph, a potential graph, okay? So I may have a graph that looks like that is first, so this section was increasing, right? So this section is increasing, going up from left to right. And then at point 1, I'm going to have to go down, right? I'm going to have to go down, right? Because this was decreasing after 1. But it first started increasing from all the way to the left to 1. But at 1, it's going to start decreasing. So take a look. We're going to call this point relative minimum or maximum. What do you think? Well, maximum, right? We're going to call that relative maximum. And what they were asking on part B is that the relative maximum occurs at x equals what value? Positive 1. Okay? It can be relative minimum if the graph is upside down. Okay? You may have a homework problem that has relative minimum, but my example that I just went over with you has relative maximum. Let's try one more that looks very similar, but I'm going to give you a g prime of x that looks like a quadratic. All right, take a look. The graph of the derivative g prime is given below. Guys, this is not g of x, this is g prime of x. Okay, that's the derivative function. Use the information in the graph to determine where g is increasing or decreasing and the values of any extrema, then sketch a possible graph of g. I always sketch first and then I talk about the relative maximum or minimum. Okay, but now let's take a look. You do know how to tell whether a function is increasing or decreasing. Anywhere above the x-axis, is where the derivative is where g, well, I'm not going to say g prime. I'm going to go ahead and say derivative is positive, right? So what part of this graph is above the x-axis, guys? Right here, this section right there. okay? And that section right there, what I just highlighted in green is where this graph has positive derivative. And positive derivative implies that the original function g is increasing, right? So let me write those two intervals. It's increasing on negative infinity to, what's the first number? -1. And the second interval is from 3 all the way to positive infinity, all the way to the right. So the function is increasing on those two intervals. All right, let's look at the below the x-axis this time, okay? Below the x-axis is where the derivative is negative, right? And we have this one U shape right here. This is where the derivative is negative because it's below the x-axis. So we know that's where the function is decreasing, right? So let's see. What's that interval? The function is decreasing on which interval? Let me write it. From -1 to +3, okay? So we're done identifying the increasing and decreasing interval for this g of x. But I'm going to go ahead and sketch a graph first. Sketch a possible graph from not f, but g. Change that to g for me. And then I'll come back and talk about which point is a relative minimum and which point is a relative maximum. So it's not going to be an exact graph because there are more than one function that will have a derivative of this function. Because you remember the constant, well, we'll talk about that later. But do just graph something like this, where you have, make sure to plot -1 and make sure to plot the +3. Remember, that's where the graph will have that turning point. It's gonna turn the direction. So first of all, I'm gonna have a graph going. Let me start with all the way on the left. This is where the graph will increase, right? Why? Because it's above the x-axis. So increase and increase over here, and this is where the graph will be decreasing. So I'm gonna go ahead and sketch a graph. So first I'm gonna have a graph, I don't know, somewhere it's gonna start going up. It's gonna start going up. And when we hit that point, -1, that's where it's going to start decreasing. It's going to start decreasing. And when it hits that 3, that's where it's going to start increasing again. So a possible graph of g will look something like this. Notice that we have a relative maximum at x equals -1, and we have a relative minimum at x equals 3, because that's where the graph started going up. And we'll talk about this idea that I'm just using like I already taught you before. This is actually the first derivative test. So you'll see more and more, but in fact, I think these are the examples that you will see, the homework problems that you will see like on toward the end of your 3.1 homework. But just wanted to kind of talk about these with you, where we talk about the derivative being positive or negative, how we can use that fact to determine where the function is increasing or decreasing. All right, let me fill in these two blanks that I didn't. Relative maximum at x equals -1, and relative minimum occurs at when x equals +3. So that's it for example 2. I may talk about critical values, and then I will stop the video and I will come back and record the rest of them, okay? All right. You've been working with this critical value so far. Take a look at the graph that we just kind of sketched. What will be the slope of a tangent line at this point? the slope of the tangent line will be 0, right? And also the slope of the tangent line at that point will also be 0. And we got those two. I mean, right there and right there. The slope of the tangent line or the derivatives were 0 at -1 and 3. That's what we... Well, one of the cases of critical value is that. Let's read this. Notice, well, I'm going to give you an example first, like a picture first, and then we will do the definition of critical values on page 3, okay? Oh no, my pencil is low on battery. All right. Consider the following graph of a continuous function f. I have 8 different points right here, right? The first couple points, I'm going to ask you to find where f of x is equal to 0. Okay, f of x equals 0. What that means is we have horizontal tangents. Horizontal tangents. Now, where do we have horizontal tangents? Right here, horizontal, horizontal, and horizontal. Now, these are the points where we have horizontal tangents. So let me write those down. At C1, at C2, C4, and, well, C7, and C8. That is, the tangent line to the graph is horizontal at these values. These are called, guys, critical values. Okay? F prime of x does not exist. Now, this time, let's find the points where the derivative does not exist. Okay, and remember, there were a couple of cases. Now, derivative doesn't exist when we have a vertical tangent. Like right here, we have a vertical tangent. Anywhere else we have a vertical tangent? No. Tangent line is vertical at that one point, C3. Okay, and where else? Where else do we not have vertical? Does not have derivative. Whenever we have sharp corners, right? Now, I have a sharp corner right here at C5. And I have another sharp corner at C6. So we don't have derivatives at C5 and C6. And the tangent line is vertical at C3. Well, I think I'm filling in these. I'm talking about the ideas, but I think the first blank right here, we were supposed to write down all these 3 points. So, because we have a tangent line at C3, we don't have a derivative. Because we have sharp corners at C5 and C6, we don't have the derivative. So that's it. I think you get something like this on your homework, but just in a picture, all these points are going to be called critical values except for the vertical tangents, okay? Any sharp corners or any places where you have a peak or a valley, then we're going to call them critical values. So let me give you the definition, okay? The definition of a critical value is any number C in the domain of f for which the tangent line at C and its opposite, f of C, is 0. So here's the first one where the derivative is 0. Or where the derivative does not exist. Okay, not the vertical. Well, no. Well, we should read the second part. The critical values are x values where relative extrema may occur. Okay, so if you look at a point where you have a vertical tangent, you really don't have a... that's not a point where the relative maximum or relative minimum may occur. So really, the C is a critical value if the derivative at C is 0 or the derivative does not exist. And in today's example, we're going to really do more and more of this first case where the derivative is 0. But if I ask you to find the critical point, I do need you to just plug in that x value back into the function and find me the order pair, the point for this. And this is something that we're going to do in our next couple examples. But this is a good point for me to stop. And I will come back and talk about finding relative maximum and minimum values. Fill out this giant table. Talk about the first derivative test and actually do a couple examples. Example 3, 4, 5, and 6. And ask you to try the classwork problems. But I'll stop the video now. I think I need to charge my pencil a little bit. And this is probably long enough for YouTube to